Hey guys, so remember in part 1 of chapter 12 we talked about different crystalline and amorphous solids. So we're going to kind of dive into that more. So there are two types of solids that are the big types, crystalline, which means they're very well ordered, and we'll see a picture in a little bit, or amorphous, which means they don't really have an order, they're kind of chaotic at the molecular level. Some examples of solids that are crystalline are like diamonds, glass. Glass is kind of iffy. Quartz, things like that. Amorphous would be more easily shaped solids like plastics, things like that. Okay, so there are 3 categories that crystalline solids will be divided into. If you want to write stuff down now, you can. There are also slides for each of these. Molecular solids. These are like normal molecular compounds. These are ones that we do IMFs for. So if we're talking about molecular solids, we're looking at their intermolecular forces, and relatively they have low melting points. Ionic solids, remember, are metal and nonmetal. Okay, these have much higher melting points. Okay, and then we have atomic solids where it's just a single element, and they vary in melting point because all elements have their own melting points. So first we're going to categorize. A is obviously ionic because it's a metal and a nonmetal. That is the easiest one to identify. Cobalt, if it is by itself, it's atomic. And then CS2 is molecular because it's 2 or more nonmetals. So you should be able to easily identify these, no problem. NH3, that would be molecular, calcium oxide is ionic, and then krypton would be atomic. Okay, so moving on, each of these have more in-depth definitions. Again, molecular solids, though, are those that make up molecules, so again, we're talking 2 or more nonmetals. That's a molecular solid. Molecular solids are held together by those IMFs, so we will determine their boiling point or melting point based on their intermolecular forces, which we talked about in part 2. Ionic solids, remember those are metals and nonmetals. They're made up by formula units, and they're held together by the attractive forces between the cation and the anion. So because the opposites are attracting, that's how they're held together. So since ionic bonds are stronger than intermolecular forces because they're true bonds, ionic solids have much higher melting points. So like salt, table salt, has a melting point of about 800. Whereas the example from before, carbon disulfide, is about -110. These are melting points. Boiling points are even higher. Atomic solids. There are lots of different atomic solids, but they all are made up by just one atom. So there will be covalent atomic solids, non-bonding, and metallic. And again, they all have their own definitions and pages. So this is just for atomic solids. Covalent ones are special. I don't want you to necessarily write anything down about these yet, but they have the highest melting points of all of them. Okay. Non-bonding are generally very low because these are noble gases only. And metallic are obviously metals, and they all have varying melting points based on their data. Okay, so covalent solids are first. Sometimes these are called network covalent. So if you, and I will call them this, I just want to make sure you're familiar with that term, network covalent. These are things that are held together by covalent bonds, like true covalent bonds. Not the in-between ones, but the ones that we draw as bonds, the lines. Okay, since covalent bonds are strong, covalent atomic solids would have the highest melting points, like diamond. Diamond is a covalent, network covalent, and its melting point is about 3,800 Celsius, which is very high. Okay, so here's our diamond, here's our structure. They're all held together. These are crystalline solids. Okay, another way to determine it's carbon or silicon with oxygen. That's how you determine, is it a covalent atomic solid or network covalent. Non-bonding, those are obviously going to be the weakest dispersion forces, and these are going to be noble gases. Okay, they have very, very low melting points because noble gases are normally gases at room temperature, so very low melting points. Metallic solids are next. Those are obviously just metals on the periodic table when they're alone, like iron, silver, lead, gold, things like that, even platinum. Melting points vary. They're in between network covalent and non-bonding. Okay, this is an important part of metallic atomic solids. So in a metallic bond, we call them, these electrons are free to move around. So we say there's a sea of electrons or an electron sea. Sometimes we also say delocalized electrons. Okay, you need to know both of those terms, sea of electrons or delocalized. That means they're not really belonging to one cation anymore. They can roam freely, which is why they're delocalized. They're not consistent to their cation. Okay, because of that, that's why metals are such great conductors and such great, they have properties like they're malleable, stuff like that. There's room for them to move around at the molecular level. All right, so we've talked about water over and over again, but really it's an amazing substance. It is very polar because of its hydrogen bonding. So it is able to dissolve polar and ionic compounds. We generally call water the universal solvent because it is highly polar. Okay. So you should also just know that liquid water expands when it freezes. So ice is less dense than water. We did talk about that in part 1, which is why ice floats in water. That's why icebergs float. That's also why fish are able to live when the lake is frozen, because the whole lake is not frozen, only the surface of the lake is frozen. So the fish are able to live during that. All right, and that's really it, y'all. So if you have any questions, please reach out. Otherwise, y'all have a great day.